so far we've been talking about Ka, our acid ionization constant. So now we're going to talk about Kb. How do we do the base ionization constant? So if we look here at our generic reaction, so you don't have to know the whole reaction, just a generic version. So if we have our generic reaction, I have a base, I have water. A base is going to gain an H+, so the H+ is going to go from my acid, which is my water, to my base. So now my acid is OH-, because remember bases create OH-, and then my base is going to have an additional H+. So that's what the reaction looks like. So then I can solve for my base ionization constant, which is going to be Kb. So we said Ka, now we're going to do Kb. So Kb is going to look the same thing. It's going to be products over reactants, but I don't include the water because the water is a liquid. So BH plus times OH minus divided by concentration of B. Now, sometimes so here my base was neutral, but my base may be an anion. So it's going to look a little different. So my water, which is my acid, this is my base, this is going to give up the H+, so I still get OH-, because that's our Arrhenius definition, is it gives up the OH- whenever it dissociates. And then I get HA, which we're used to thinking of HA as my acid, so just don't get confused by that. HA can be my acid notation, or it can be my conjugate acid of my base. So still an acid, just might be, because this is my base, this would be my conjugate acid. So it could be a conjugate acid versus just the acid I'm starting with. So Kb here would be HA times OH-. Water doesn't count, A-. So those are my generic ways of writing my base ionization constant. All right, so we already talked about POH and how to solve POH if it's a strong base, etc. So now let's talk about how to determine the OH- and the pH when it might not be. So let's look at this problem. It says determine OH- and pH of a 0.06 dimethylamine solution at 25 degrees Celsius. The Kb is 5.9 times 10 to the negative 4. And I went ahead and gave you the reaction, but if you notice, this is just my B plus my water going to my BH plus my OH-. So this is the exact same thing as our first one right here. Okay? But I was nice and I gave it to you. All right, so what are we looking for in this problem? So I'm looking for, I'll write it down here. Determine the OH-, okay, and pH. And what do they give me? So they gave me 0.060 molar of the dimethylamine. So we could just say dimethylamine, DMA. It's actually the shorthand for it anyway. And 25 degrees Celsius, Kb, 5.9 times 10 to the negative 4. All right, so now we go, okay, I need the OH- concentration. And so what we would do, say it was like NaOH and it was 0.05, we would say, okay, well that goes to Na plus OH-, it's 1 to 1. So I have the exact same amount of this as this, and there's my concentration. But I can only do that because this guy is strong. Same thing we just talked about with the acids. Okay? So to figure out if I can do my short, fast way with this guy, I have to know what dimethylamine is. So just like I said in the last lecture, go to your chart and see if he's in there. Okay? So if you go to your chart, you're going to see that dimethylamine is not one of the ones in your chart. So if it's not in the chart, what did I say to do? Go ahead and assume that it's weak. Okay? So we're going to go ahead and assume that he is a weak base. Which has got kind of a low number here, so that makes sense for his Kb. So if he's a weak base, then can I just automatically find the OH that way? What will I have to do? An ice table. The exact same thing we had to do before. So if it's not if it's not a strong and it dissociates partially, and the fact that they gave me the equation with the double arrow also tells me it's weak, so it's really trying to help me. So when they give me this equation with this double arrow, it's telling you this is weak, this is not the easy way. Okay? So since it's not the easy way, we have to do a ice table. Okay? So first I gotta figure out is how much B did I start with? It said 0.06. Water doesn't count. Same process. It's gonna be very similar to what we just did in the last problem, in the last lecture. 0, 0. It's all a 1 to 1, so 1 to 1 to 1 to 1. So this is gonna be negative x plus x plus x. So this is 0.06 minus x, x, x. Okay? So what I'm trying to figure out is I want the OH minus concentration. I want to know what x is. So if I want to know what x, I have to use what else they gave me. They gave me the Kb. So I'm going to use the Kb to find x. So I need to write my Kb. So my Kb was my BH plus times my OH minus over B. Plug in the stuff, I get 5.9 times 10 to the negative 4 is equal to x times x divided by 0.06 minus x. See how it's very, very similar to the problem we just did, except we're talking about bases. That's the only difference, really. All right, so let's kind of simplify that a little bit. 5.9 times 10 to the negative 4 is equal to x squared divided by 0.06 minus x. So yet again, it would be great if we could get rid of this x. So for our approximation, here are my rules. X has to be a lot less than 0.1. Kb has to be very small. Percent ionization less than 10%. So Kb is 0.4. So that's small, so we can say, yep, good there. Remember, I can't check the other ones until I do the problem. So go ahead and assume that that's going to be okay, and we'll confirm it at the end. 5.9 times 10 to the negative 4 is equal to x squared divided by 0.06. Multiply that over, and you get 3.54 times 10 to the negative 5 is equal to x squared. Square root, and we get x is 0.0059. So now we could do our next assumption. This had to be, the x had to be less than 0.1. It's 0.0059. So yep, we're good there. So let's go back to what we were trying to find. The first thing we wanted to find was our OH minus concentration. OH minus concentration is in my table, that's x. So if I have x, I have OH minus. So we know OH minus was x, so that's the 0.0059 molar, because it's concentration. So I got the first answer. Okay, the next thing I want is pH. So it says pH, not pOH. So I need pH. Well, we know pH is negative log of the hydronium ion. So there's two ways you could do this. You could use your Kw, OH minus times H3O plus, plug in the 1 times 10 to the negative 14 and the OH here, and then solve for H3O plus. You could do it that way. But you're more likely to make a math error. So what I would rather you do is go ahead and use your OH to find your pOH. So we know this is negative log of your OH minus, because this is going to make it where you have less exponents and funky numbers, and so they're smaller, you're less likely to make a math error. So we plug that in. 0.0059. You get your pOH to be 2.23. So then we want the pH. Well, we need pOH plus pH is equal to 14. So this is 2.23. So my pH is going to be 11.77. All right, so now I got that. the last thing we said we wanted to do, and there's more blank slides if you want it, but I'm just going to do it right here. The last thing we have to do before we say we're sure that these are correct is we have to check our percent ionization. We've already checked our X, we've checked our Kb, now we need our percent ionization. So percent ionized is X over initial times 100. So my X was 0.0059. My initial was the 0.06, right here, 0.06. So that's going to give me 9.83%. So it's close, but it's still under. So since it's still under, we're good, and we're for sure that these are going to be my final answers. Okay? So that's how you do it if it's a base. So it's very, very similar to the thing that we just did with just being an acid. Now we can compare it and try to figure it out if it's a base. All right. So the next thing we want to talk about is, now that we've talked about how to use KBs, and last class we talked about using the Ka, how do these two relate? How do Ka and Kb relate to each other? So let's look at this. So here is a big table with a bunch of different Kas and Kbs. So you got Kas, you got Kbs. So let's look. For this acid, it has a large Ka, but for his conjugate, so here's this acid, here's his conjugate base, the Kb is really small. Here, methane has a very small Ka and a really large Kb. Okay? So what we should notice is that they're opposite. Okay? So if the Ka is really high, its associated Kb would be very small. So if Ka is high, Kb is going to be low. Like we talked about with the conjugates, if it's a strong acid, his conjugate would be a weak base, vice versa. So that's why we see if it's strong, it's weak, and vice versa. So when we want to compare, I might give you a list of them and I ask you to compare them. The larger the Ka, the stronger the acid. So these guys are strong acids. Larger the Ka, stronger the acid. The larger the Kb, the stronger the base. So these are strong bases. So the bigger the number, the stronger it is for whichever one that is. So if it's a big Ka, it's a strong acid. If it's a big Kb, it's a strong base. Okay? So it corresponds, the larger the number, the stronger it is for whichever one it goes with. All right, so let's talk about their relationship. So we know that an acid with its conjugate base pair, an acid-base conjugate pair, is related to each other. Okay? So let's talk about how they're related to each other. So he's going to have a Ka and he's going to have a Kb. What happens if I multiply those two together? So let's write out the Ka. So we said Ka is the H3O plus times A minus over HA. Kb would be the HA over OH minus over A minus. Now, I'm using the anion because my conjugate base here is an anion. So remember when we wrote the Kb's, there was one for neutral and one for anion? I'm using the anion because this is an anion. So when I multiply them, what happens? You notice the A minus cancels, HA cancels. The only thing left is the H3O plus and the OH minus. So my Ka times my Kb is equal to H3O plus times OH minus. And what did we also know that's equal to? Yeah, so remember we said Kw was H3O plus times OH minus. And we said that Kw was equal to 1 times 10 to the negative 14. So if I have the Ka, I'm trying to find the Kb. If I want to know how these relate, it's also equal to 1 times 10 to the negative 14. So that's the equation you want to know. So you want to know this, that Ka times Kb is equal to 1 times 10 to the negative 14. That's how they relate. So if you have one, you can find the other. Because depending on what type of reaction you're doing, you might want the Ka or the Kb. So here, when we were doing these, if I'm trying to find the OH minus, I had to have Kb. If I'm trying to find the pH and the H3O plus, I need the Ka. So it has to match. So sometimes you need to be able to convert from one to the other. All right, so let's do this problem. So phenol C6H5OH is a weak acid. Here's my Ka at 25 degrees Celsius. Calculate Kb for the phenolate ion. So what am I looking for? Kb. So it says calculate Kb for the phenolate ion. What do they give me? So they gave me Ka, and I said it was at 25 degrees Celsius. That's it. So they gave me Ka, and they want to know Kb. That's it. So if I only have Ka and they want to know Kb, I need to know how they relate. So I said, oh, okay, well, Ka times Kb is equal to 1 times 10 to the negative 14. So I can plug it in. Make sure you use your parentheses when you divide this over, and you get that Kb is equal to 7.7 times 10 to the negative 5. And double check it. Go ahead and multiply your Kb that you found by your Ka, and make sure you can go backwards. Because if you put it in your calculator the wrong way and then you try to go backwards, you won't get the Kw, the 1 times 10 to the negative 14. So always make sure you can go backwards and still find that. All right, so now we've done bases, Kb's, and we've talked about how Kb and Ka relate. So next lecture, we're going to talk about salts.